Okay, we've all been there, right? Staring at a data table, maybe for engineering or science or finance, and the exact value you need, it's just not there. Well, today, we're going to talk about a super simple but incredibly powerful tool to solve that exact problem. It's called linear interpolation. So, picture this. You're deep into a problem. Maybe you're working with a steam table for thermodynamics class. You've got the number for point A, and you've got the number for point C, but the one you actually need is point B, sitting right there in the middle, in a gap in your data. What do? Just guess? No way.
So here's our game plan for this explainer. First, we'll really define that missing data problem. Then, I'll introduce you to our solution, linear interpolation. We'll look at the formula itself, and then we'll walk through a real-world example, step by step. And we'll finish up with a super important final check that's going to save you from some really common headaches.
Okay, let's zero in. This is the heart of it, right? We have solid known data points. We know what's happening at point A, we know what's happening at point C. The challenge, the whole puzzle, is figuring out the precise value of that point B that's sitting somewhere on the line between them. Let's make this totally real. We'll use a classic example with a steam table. Let's say we know the enthalpy of a saturated liquid at 40 bar of pressure, and we also know it for 42 bar. But the thing is, our calculation needs the enthalpy at exactly 41 bar, and if you look in the table, it's just not there. So we've got to find it ourselves.
So how do we do it? Well, the solution is this fantastic technique called linear interpolation. It's basically a way for us to make a really smart and accurate estimate for that missing value.
You know, the magic of linear interpolation comes from one really simple but powerful assumption. We're going to assume that the relationship between our two known points is just a straight line. And once we make that assumption, we can find any value that falls in between them with a whole lot of confidence.
All right, let's pop the hood and look at the formula that makes all of this work. Don't let it scare you. It's really just a simple proportion. All we're doing is comparing the ratios of the differences between our data points.
And the logic here is actually pretty cool and intuitive. What this formula is saying is that the position of your target value on one scale, let's say it's halfway between the low and high numbers, well, it has to be in the exact same relative position on the other scale. It has to be halfway there too. We're just setting those two fractions, those two ratios, equal to each other. That's it.
Okay, enough theory. Theory's great, but let's get our hands dirty and actually put this thing into practice. We're going to take that formula and use it to solve our steam table problem and finally find that missing enthalpy value at 41 bar. Let's do it.
All right, step one. And listen, this is absolutely the most important first step. Before you even think about plugging numbers into a formula, you've got to get organized. We need to clearly write down the data we have, our knowns, and then pinpoint exactly what it is we're looking for, our unknown.
So here's our setup, all laid out. Look on the left, you've got pressure. We know the values for 40 and 42 bar. Our target is 41. Now look on the right. We have the matching enthalpy values, and our mission right now is to solve for that big question mark. Okay, now for step 2. We're going to build our equation. And the method is super simple. It's all about subtraction. For each side of our table, we're going to create a ratio that looks like this. Target minus low divided by high minus low. So we just plug in the numbers. For the pressure side on the left, that becomes 41 minus 40, divided by 42 minus 40. Simple enough. Now the right side for enthalpy has to look exactly the same but with H as our unknown. So it's H minus 1087 divided by 1102 minus 1087. See? The structure is identical. And you know what? We've done the hard part. From here, it's just a bit of straightforward algebra. All we've got to do is rearrange that equation just a little bit to get H all by itself. So, after we do the math, we crunch the numbers, and bam! We've got our answer. The estimated enthalpy at 41 bar is 1090.75 kilojoules per kilogram. We've got our number. But wait, hold on, we are not done yet. I'm serious. There is one final, incredibly important step that you should never, ever skip. It's the quick little sanity check that will stop you from making simple but really costly mistakes. And here is the golden rule for this check. It's so easy. Your final answer has to, it must, fall somewhere between your starting low value and your starting high value. If your answer is higher than the high or lower than the low, you know you've made a mistake somewhere in the math. So let's do that check right now. Our low enthalpy was 1087. Our high enthalpy was 1102. And our calculated answer? 1090.75. Does it fit? Yes. It falls perfectly and logically right in between those two numbers.
That tells us our calculation is solid. We're good to go.
Okay, so let's just quickly recap the big ideas. Number 1, linear interpolation is your go-to tool for filling in those gaps in your data. Number 2, the whole method is built on setting up a simple ratio of differences. And number 3, never, ever forget to do that final logic check to make sure your answer actually makes sense.
You know, we focused on a thermodynamics example today, but this technique is like a Swiss Army knife. It's used everywhere, in finance and computer graphics, all over engineering, you name it. So the final question I want to leave you with is this. Now that you've got this technique down, where in your world, in your field, can you put this powerful estimation tool to work?